Hi and welcome to this tutorial on the ideal gas equation. In the last tutorial, we learnt about the mole and its relation to Avogadro's constant, and we learned how to perform calculations. We looked at water crystallization and various other calculations that we can use with moles. So here we're going to have a look at the ideal gas in more detail, the understanding of the ideal gas equation, and unit conversions, which are a really big part of this topic. So ideal gas, it's a hypothetical gas whose volume varies in proportion to its temperature and inversely varies in proportion to its pressure. So the ideal gas equation puts these concepts together. So it's used to calculate the number of moles found in a specific volume of gas. So we have to use the ideal gas equation when we don't have room temperature and pressure or standard temperature and pressure. Okay, so in the previous tutorial, we had to look at when we're in room temperature and pressure, we know that 1 mole of gas occupies 24 decimeters cubed of space. But what if it's not room temperature and pressure? We have to use the ideal gas equation to help us work out how many moles we have. So characteristics of an ideal gas, we've got a lack of intermolecular forces. So they neither repel nor attract each other. We've got elastic collisions. So no energy is lost when particles collide against each other or against the walls of the container. So the kinetic energy in total stays the same. Okay, so that's an important characteristic. And then finally, we've got zero particle volume. So the individual gas particles, they're so small in comparison to the empty space around them that their volume is negligible. So those are all the assumptions really we're making here. So a real gas is a gas that doesn't satisfy the conditions for being an ideal gas. So no gas can behave exactly like an ideal gas, but the lower their intermolecular forces, the more they can approach that ideal behaviour. So the ideal gas equation, it's used to calculate the number of moles found in a specific volume of gas. And this is the easiest format to remember it in, and then you can just rearrange. So PV equals N RT. So as long as you know what those letters mean, you can learn them and then you can just rearrange it to mean whatever you want. So P here, you can see my units under here. P is equal to pressure and it has to be in pascals. We often work with kilopascals. You need to know it's got to be in pascals. Volume is in meters cubed, not decimeters cubed. Remember in the previous tutorial, we were using decimeter cubed a lot. So that's something that you really need to remember and people can fall up on. And then we've got N is, of course, number of moles. I use that quite a lot to mean moles. R is 8.31. That is given to you in your data table, but it is a number that really should be off the top of your head. And temperature is in Kelvin, not degrees Celsius. So there's a few sort of new units here, sort of things that we need to make sure we're okay in terms of converting. So have a look at these questions here. Give it a go yourself. Can you convert these units into the ideal gas standard units that you'll need? So we've got 20 degrees Celsius. How do we convert that to Kelvin? Well, you can see on this slide here that to get from temperature from degrees Celsius to Kelvin, we have to add 273. So 20 plus 273 is 293 Kelvin. Question 2, what is 800 centimeters cubed in meters cubed? So let's jump to our table. If we want to go from centimeters cubed to meters cubed, we need to divide by 1,000,000, 10 to the 6. We've got centimeters cubed to decimeters cubed to meters cubed. And each of these, sometimes it's quite handy to have these, is a power of 10 to the 3. I shouldn't even have times, a 10 to 3, whether you divide or times. So in order to make the colossal jump all the way from centimeters to meters, it's 10 to the 6, okay? Now, there's not gonna be many centimeters cubed in a meter cubed, so we're gonna divide that number by 1,000,000. So 800 divided by 10 to the power of 6 is 0.0008 meters cubed. Wow. What is 5 decimeters cubed in meters cubed? So I'm jumping back up to here. So I'm going from decimeters and meters. So it's going to be to the power 10 to the 3. Now there's decimeters cubed is a smaller volume, so we're going to divide it. So 5 divided by 1,000 or 10 to the 3. is 0.005 meters cubed. And what is 0.5 kilopascals and pascals? That one's quite easy because we've seen how many grams are there in a kilogram is 1,000. So there are 1,000 pascals in a kilopascal. So we're going to have to, if we've got 0.5 kilopascals, we can times that number by 1,000 to get us the number in pascals. So 0.5 times 1,000 is 500 pascals. So here it is summarised in the table here, these sort of conversions. I do find, as you saw in the previous slide, drawing centimetre cubed, centimetre cubed, meters cubed, and understanding that they're all 10 to the 3, and you can use indices, that really helps me remember how to convert. Remember to look out for units. This is the really, really big area that people slip up on ideal gas equations, is incorrect conversions. You need to remember the units that they need to be in, that it has to be in pascals and meters cubed, and you also need to remember how to convert. So if you're not given the units in the table, of course, you'll have to convert them. So have a go at a question yourself. Here's a practice question. Pause the video, give it a go. So something that you can do if you've got time, chemistry exams can be quite tight for time, but you can write out the values as you're given in the questions. Okay, so we've got our volume is 1,250 centimetres cubed. Our temperature, our value for T, because of course we're using PV equals nRT. Our temperature is 45 degrees Celsius. Our pressure, our value for P, is 105 kilopascals. Oh, there's a lot of converting needed here. Our mass is 2.4 grams. And our value for R, I'm going to check, but if it's not given, it's going to be what's in our data sheet, which is 8.31 joules per Kelvin per mole. Okay, if it's not given to you, but it is given to you, use the value in the question if it is. Now I'm going to convert my values. So volume, I need to convert 1,250 into meters cubed. So I'm going to divide it by 1,000. I'm going to divide it by 1,000,000. Sorry, cut that. Divided by 1,000,000, or 10 to the 6. And that's going to give me 1.25 times 10 to the minus 3. My temperature is I need to add 273, so 45 plus 273 is going to convert it to Kelvin, so it's 318 Kelvin. My pressure needs to be in pascals, so I'm going to convert from kilopascals to pascals. I need to times by 1,000, so 105 times 1,000 is 105,000 pascals. And my mass is the same. That's not going to change, and my R is the same. They don't need any converting. We're not even going to use mass in that original question. We might need it later on. Then I'm going to rearrange. So I'm going to write my ideal. So PV equals nRT, but I'm going to rearrange it, and you do get marks for this without any numbers, just the rearranging. So don't forget to actually write down your working. Ideal gas questions are never, or very rarely are they, give the student the answer on the line, meaning we don't just look at the number and give you a tick and give you all the marks if the number's correct, because there are ways that you can fluke the correct answer with incorrect conversion. So as examiners, we always look and check every single conversion and all of your rearranging. So it's one of those examples where you have to show your working, otherwise you won't get the marks, even if the answer on the line is correct. So N equals PV divided by RT, that's just rearranged. So then let's work out N. So N equals P. What's my value for P? It was 105,000 pascals times V, volume, which was 1.25 times 10 to the minus 3. So that's the top of my equation, divided by R, 8.31, times my Kelvin value, which was 318. So that has given me an answer of 0.0497 moles. And that's 3 significant figures, of course. But I'm going to keep the true value in my calculator. And finally, calculate the relative molecular mass. So N equals moles equals mass over MR. So now I've been asked to work out the MR. So MR is equal to mass over moles. So the MR is going to be equal to my mass, which was given to me in the question, 2.4, divided by the number of moles that I calculated above, 0.0497. And that is 48.3 grams per mole, because that's the unit of MR. And that is your answer.